Twisting multiple ground wires together using a cordless drill is not an acceptable practice according to electrical codes and industry standards. There are several drawbacks to this method. Firstly, there is poor electrical connection. Twisting wires together creates an unreliable connection that can lead to loose strands, high resistance, and increased voltage drop. This can result in overheating, arcing, and potential fire hazards. Secondly, code violations occur. Electrical codes in most regions prohibit twisting wires as a method of splicing or connecting them. These codes require proper terminations such as solder joints, crimp connectors, or wire nuts to ensure safe and secure connections. Thirdly, it is difficult to inspect and maintain twisted grounds. Twisted grounds can be difficult to inspect for loose strands or poor connections. This can make it challenging to identify and repair any issues that may arise over time. Fourthly, there is an increased risk of short circuits. If the twisted ground wires come into contact with each other, it can create a short circuit, causing an overcurrent condition and potentially tripping circuit breakers or damaging equipment. Instead of twisting ground wires together, it is recommended to use the following methods for proper termination. One method is solder joints. Solder the ground wires together using a soldering iron and solder. Another method is crimp connectors. Use insulated crimp connectors specifically designed for grounding applications. Insert the wires into the connector and crimp them tightly using a crimping tool. Another method is wire nuts. Twist the individual ground wires clockwise together, then secure them using a wire nut. Ensure the wire nut is properly sized and tightened to provide a strong and secure connection. By following these recommendations, you can ensure safe and code-compliant grounding practices in electrical installations. A good grounding system is essential for electrical safety and the proper functioning of electrical equipment. It provides a low impedance path for fault currents to return to the source, minimizing the risk of electrical shock and fire hazards. The grounding system should be designed and installed according to the applicable electrical codes and standards. Proper grounding helps to stabilize voltage levels within an electrical system. It prevents voltage fluctuations and transients that can damage sensitive electronic equipment. A stable voltage supply ensures reliable operation and extends the lifespan of connected devices. Effective grounding minimizes electromagnetic interference, or EMI. EMI can disrupt the operation of electronic devices and cause data corruption. A well-grounded system helps to contain and dissipate EMI, preventing it from interfering with other equipment. Grounding is not just about safety. It also plays a crucial role in the proper functioning of electronic equipment. Many electronic devices rely on a stable and reliable ground reference for accurate signal processing and data transmission. Without proper grounding, these devices may malfunction or produce inaccurate results. When designing a grounding system, it's essential to consider the specific requirements of the electrical installation. Factors such as the size of the building, the type of equipment being used, and the soil conditions can all influence the design of the grounding system. A qualified electrical engineer should be consulted to ensure that the grounding system meets all applicable codes and standards. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Brown connections can corrode over time, reducing their conductivity and compromising the integrity of the grounding system. Regular inspections can identify and address any issues before they become a safety hazard. Grounding electrodes, often made of copper or galvanized steel, are buried in the earth to provide a connection to ground. These electrodes should be installed below the frost line to prevent damage from freezing and thawing. The number and spacing of grounding electrodes will depend on the soil resistivity and the size of the electrical system. Grounding conductors, typically made of copper wire, connect the grounding electrodes to the electrical equipment. These conductors should be sized according to the applicable electrical codes to ensure that they can safely carry fault currents. Grounding busbars are used to provide a central point for connecting grounding conductors. These busbars should be made of a conductive material such as copper or aluminum and should be securely mounted to the building structure. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect against electrical shock. GFCIs monitor the current flowing in a circuit and quickly disconnect the power if a ground fault is detected. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Surge protective devices, or SPD, are used to protect electrical equipment from voltage surges. SPD divert surge currents to ground, preventing them from damaging sensitive electronic components. SPD should be installed at the service entrance and at other locations where surge protection is needed. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault currents. Bonding helps to minimize voltage differences between metal parts, reducing the risk of electrical shock. All metal enclosures, conduit, and equipment should be properly bonded. Static electricity can build up on non-conductive surfaces, such as carpets and clothing. Static discharge can damage sensitive electronic equipment and can also be a fire hazard in certain environments. Grounding can help to dissipate static electricity, reducing the risk of static discharge. In hazardous locations, such as areas where flammable materials are present, grounding is essential to prevent explosions. Grounding helps to prevent the buildup of static electricity, which can ignite flammable vapors. Special grounding requirements apply in hazardous locations. Electrical codes provide specific requirements for grounding electrical systems. These codes are designed to ensure the safety of people and property. It is important to be familiar with the applicable electrical codes and to follow them carefully when designing and installing electrical systems. Proper grounding is an essential part of electrical safety. By following the recommendations outlined, one can ensure safe and code-compliant grounding practices in electrical installations. Grounding is a critical aspect of electrical safety, and understanding its principles and best practices is essential for anyone working with electrical systems. A ground fault occurs when an unintended electrical path develops between a live conductor and ground. This can happen due to damaged insulation, loose connections, or accidental contact with a grounded object. Ground faults can be extremely dangerous, as they can cause electrical shock and fire hazards. A ground fault circuit interrupter, or GFCI, is a safety device that is designed to protect against electrical shock from ground faults. GFCIs monitor the current flowing in a circuit and quickly disconnect the power if a ground fault is detected. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of ground faults. When a ground fault occurs, a GFCI can trip in a fraction of a second, preventing serious injury or death. A surge is a sudden and temporary increase in voltage in an electrical system. Surges can be caused by lightning strikes, power grid switching, or the operation of heavy electrical equipment. Surges can damage sensitive electronic equipment and can also cause fires. A surge protective device, or SPD, is a device that is designed to protect electrical equipment from voltage surges. SPD diverts surge currents to ground, preventing them from damaging sensitive electronic components. SPD should be installed at the service entrance and at other locations where surge protection is needed. Electrical bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault currents. Bonding helps to minimize voltage differences between metal parts, reducing the risk of electrical shock. All metal enclosures, conduit, and equipment should be properly bonded. Static electricity is an electrical charge that builds up on the surface of a material. Static electricity can be generated by friction, such as when you walk across a carpet or comb your hair. Static electricity can be annoying and can also damage sensitive electronic equipment. Grounding can help to dissipate static electricity, reducing the risk of static discharge. In hazardous locations, such as areas where flammable materials are present, grounding is essential to prevent explosions. Grounding helps to prevent the buildup of static electricity, which can ignite flammable vapors. Special grounding requirements apply in hazardous locations. Electrical codes provide specific requirements for grounding electrical systems. These codes are designed to ensure the safety of people and property. It is important to be familiar with the applicable electrical codes and to follow them carefully when designing and installing electrical systems. The National Electrical Code, or NEC, is a widely adopted standard for electrical installations in the United States. The NEC provides detailed requirements for grounding electrical systems, including the size and type of grounding conductors, the installation of grounding electrodes, and the bonding of metal parts. The NEC is updated every 3 years to reflect the latest advances in electrical technology and safety practices. State and local electrical codes may also have specific requirements for grounding electrical systems. It is important to check with the local authorities to ensure that all electrical installations comply with the applicable codes. There are many different types of grounding electrodes that can be used in electrical systems. The most common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. Ground rods are typically made of copper or galvanized steel and are driven into the ground to provide a connection to earth. Ground plates are flat metal plates that are buried in the ground to provide a connection to earth. Concrete encased electrodes are grounding conductors that are embedded in concrete foundations or footings. The choice of grounding electrode will depend on the soil conditions, the size of the electrical system, and the applicable electrical codes. Grounding conductors are used to connect grounding electrodes to electrical equipment. Grounding conductors should be sized according to the applicable electrical codes to ensure that they can safely carry fault current. Grounding conductors are typically made of copper or aluminum. The size of the grounding conductor will depend on the size of the circuit and the type of equipment being grounded. Grounding busbars are used to provide a central point for connecting grounding conductors. Grounding busbars should be made of a conductive material such as copper or aluminum and should be securely mounted to the building structure. Grounding busbars provide a convenient way to connect multiple grounding conductors and to ensure that all grounding connections are properly made. The resistance of the grounding system is an important factor in determining its effectiveness. The lower the resistance of the grounding system, the more effectively it will be able to dissipate fault currents. The resistance of the grounding system should be measured periodically to ensure that it is within acceptable limits. There are several methods that can be used to measure the resistance of the grounding system. The most common method is the 3-point fall of potential method. The 3-point fall of potential method involves driving 2 auxiliary ground rods into the ground and measuring the voltage drop between the grounding electrode and the auxiliary ground rods. The resistance of the grounding system can be calculated from the voltage drop and the current flowing through the grounding electrode. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Ground connections can corrode over time, reducing their conductivity and compromising the integrity of the grounding system. Regular inspections can identify and address any issues before they become a safety hazard. Grounding is not a one-time task. It is an ongoing process that requires regular attention and maintenance. By following the recommendations, one can ensure that electrical systems are properly grounded and that people and property are protected from electrical hazards. Proper grounding is a fundamental aspect of electrical safety and should be taken seriously by everyone working with electrical systems. Grounding is a critical safety measure that protects people and equipment from electrical hazards. It provides a low resistance path for fault currents to flow back to the source, tripping circuit breakers or fuses and preventing electrical shock. Without proper grounding, fault currents can flow through unintended paths, such as through a person's body, causing serious injury or death. The grounding system consists of several components, including grounding electrodes, grounding conductors, and bonding connections. Grounding electrodes are typically metal rods or plates that are buried in the earth to provide a connection to ground. Grounding conductors are wires that connect electrical equipment to the grounding electrode. Bonding connections are used to connect all metal parts of the electrical system together to create a low impedance path for fault currents. The size and type of grounding conductors and electrodes are determined by the applicable electrical codes. It is important to follow these codes carefully to ensure that the grounding system is properly installed and will provide adequate protection. There are several common grounding mistakes that can compromise the effectiveness of the grounding system. One common mistake is using undersized grounding conductors. Undersized grounding conductors cannot safely carry fault currents, which can lead to overheating and fire hazards. Another common mistake is failing to properly bond all metal parts of the electrical system together. Improper bonding can create high impedance paths for fault currents, which can increase the risk of electrical shock. Another common mistake is neglecting to inspect and maintain the grounding system regularly. Ground connections can corrode over time, reducing their conductivity and compromising the integrity of the grounding system. Regular inspections can identify and address any issues before they become a safety hazard. Proper grounding is not just a matter of following the electrical codes. It also requires a thorough understanding of the principles of grounding and the potential hazards associated with electricity. Anyone working with electrical systems should receive proper training in grounding techniques and safety procedures. Grounding is an essential aspect of electrical safety, and it should not be taken lightly. By following the recommendations, you can ensure that your electrical systems are properly grounded and that you and others are protected from electrical hazards. Remember to always consult with a qualified electrician for any electrical work. They have the knowledge and experience to ensure that the work is done safely and in compliance with all applicable codes. Grounding is a complex topic, and it is important to stay up to date on the latest codes and best practices. The electrical industry is constantly evolving, and new technologies and techniques are being developed all the time. By staying informed, you can ensure that you are using the safest and most effective grounding methods available. Grounding is an investment in safety. A properly grounded electrical system will protect people and equipment from electrical hazards and will provide peace of mind knowing that you have taken the necessary steps to ensure electrical safety.